This is what we have to prove. So the proof will be by contradiction. So pick up a cycle in Sn minus Hik, which is not a boundary. Okay, alpha is a cycle, but it is not a boundary. So then it is not a boundary in at least one of A or B. Yeah, because Sn minus Hik is induced from A and B. So it is not a boundary in at least A or B. Yeah, that is very clear. So what should we do now? So we need Hik. So we construct a nested sequence in the last coordinate. Yeah, so we have seen before we constructed Ik minus 1 times 0 to half. So now we have Ik minus 1 times I1 or Ik minus 1 times I2, I3 and so on. So we are constructing a nested sequence of intervals, especially in the last coordinate. Yeah, so instead of 0 to half, we are trying to have these smaller and smaller intervals. So we could say instead of 0 to half, we have 0 to 1 by 4, 0 to 1 by 8, yeah, so on, 1 by 16, 0 to 1 by 32 and so on. So, or you could just construct any shrinking sequence. So shrinking to a point P, yeah, the sequence is shrinking to a point P. So now we have already assumed that alpha is not a boundary. So alpha is not a boundary in Sn minus Hk minus 1 times Im for any m. So this is our assumption, yeah, alpha is not a boundary. So it will not be a boundary in so alpha is not a boundary in Sn minus H Ik minus 1 times Im. Yeah, because we have said it is not a boundary. So this is true for all m. Yeah. So for any m, this is true. This is our assumption. So I'm just giving an example. Im before we had taken as 0 half and half 1. So now we take any shrinking set. Basically we want to isolate a point P by shrinking this further and further down. So you could take any smallest possible Im and then say alpha is not a boundary in this thing. Okay, now we write the contradiction part. So on the other hand, you know alpha is a boundary of a chain beta. So alpha is a boundary of a chain beta in Sn minus Hik minus 1 times P. So this is Ik minus 1 times P. Now this was from our inductive step. We know the reduced homology group of this is 0. As we saw before, you take a point out of the sphere Sn, it becomes isomorphic to Rn, which is equivalent to a contractible space, which gives you 0. This is precisely because the homology group of this is 0, and that essentially means that every cycle is a boundary. So since alpha is a cycle, it is boundary of some chain for a point P. So now you can see how the contradiction is going to arise. So what is this beta? What is this chain beta? Now chain beta, we know all these chains in chain complexes are nothing but combination of singular simplices. So it is a finite linear combination of singular simplices with compact image. And all of them lie so all of these simplices lie in Sn h ik minus 1 times Im. So the union of these images, so all these images lie in this part, and the union of these images is covered by the nested sequence of open sets. So now you get the contradiction. So you said that alpha is a boundary of a chain because we just had proved on the previous slide that the reduced homology is 0. And now this chain beta also exists in Sn minus hik minus 1 times Im. And we had written just above that now alpha is not a boundary, and then we have just shown that alpha is a boundary in Sn minus hk minus 1 times Im. So see, first we have written now alpha is not a boundary in Sn minus hik minus 1 times Im, and now we show that alpha is a boundary of a chain beta which lies in Sn minus hik minus 1 times Im, and this is a contradiction. So first we show alpha, that is pretty much it. We say alpha is not a boundary, and then we see that alpha is a boundary of a chain in the same set of interval. And that is pretty much it.